Record. Um, does anybody want to look at anything from the homework or the quiz from over the weekend?
Yes, can we look at number 5 on the homework?
Sure. Give me a second to find it and open it. This is not your class. Let's go into the right class. And let's go into my labs. And let's go into course home. And in course home, let me go to course tools. And course tools, let me go to assignment manager. And then let me see. You're looking at homework 7 or 8, hon?
8, please.
And that was the permutations and combinations. Home.
Yes.
And you wanted to see question number which?
5.
Okay. Do that. Question number 5. I feel like I'm juggling too many things. Okay, question number 5 was a combination. 8C5. Are we looking at the right one, huh?
Yeah.
Okay, first of all, you have a scientific calculator.
I don't have a scientific calculator. I've been trying to do everything from my phone
Okay.
calculator.
Let me look at my phone calculator real quick. Although I would prefer you not use a phone as a calculator because, well, the rule goes don't use a phone as a calculator because on in-class tests, we don't want you using a phone because we don't want you to use internet connectivity. All right, let me see. When my calculator is sideways, it's scientific, but I am not seeing permutations and combinations, so that does us no good. So over here, when I'm looking at doing it without a calculator, 8 combination 5, that would be, when it's a combination, there's a denominator. So I've got 5 factorial in the bottom, 5, 4, 3, 2. And then in the numerator, I have a permutation 5, or basically I'm going to start with the number 8. I'm going to work it the same number of factors in the numerator as denominator. So 5 on the bottom, 5 on the top. So far, are you with me?
Yes.
Okay, so now I can cross out common factors. The 5s can cancel, the 4s can cancel. And now if I were to do totally by half, I would also say 3 times 2 is 6. And so that leaves me with 8 times 7, which is 56.
Okay.
If you're doing it totally by hand and you don't want to write as much, when we were looking at combinations the other day, we said there was a little bit of a shortcut. 8 combination 5 would be the same as 8 combination 3 because 8 minus 5 is 3. And if you do it that way, well, people using calculators, that's a useful shortcut. People doing it by hand, because you see already it's made it a much easier problem.
Oh, okay.
Okay.
Yeah, that makes a lot more sense.
So if this number is ever more than half of the larger number, take the difference. It gives you less work.
Okay, thank you.
I'm thinking most people in class are doing it by calculator and they don't need that. But if you're doing it without a calculator, that's the way to go. Okay. I'm going to clear this. Does anybody else want to look at anything in the homework?
Was homework 10 on that note listed there?
I don't remember. Let me go back. I'm going to be totally honest with you. I don't remember. I'm going to change my finger back into a mouse. Homework 10 is not due until the 14th, so we're kicking the can way down the road with that one.
Okay.
Okay.
Oh,
So we will eventually get there. I think that's the probability with permutations and combinations, which is what's going to be the lion's share of what we talk about today.
yeah. Okay.
And that is where probability gets most involved for people. And, you know, they just looking at that stuff. Anybody else want to look at any other homework? If not, I'm going to get rid of that toolbar. I'm going to make sure that there's nobody still in the waiting room. Those of you that I just letting, if you could stick around for a minute at the end of class and make sure that I did get the fact that you did come in, so that we're not all waiting for me to redo attendance. So we left off with that phrase empirical probability, and we didn't really define it. So let's go through and start by defining that. Oops. Is it possible for everybody? When we define probability, we defined it in terms of the number and the total number of samples.
I'm sorry, but it's kind of hard to, you're like cutting out or something.
Okay, let me get my headphones. Adam, is that better?
Much, yeah.
Okay. Thank you for letting me know.
Mm-hmm.
And I have way too many things on this. Okay, so we can get it out of the way. Okay, so empirical, we had defined the theoretical probability of an event as the number of ways the event can occur over the number of things in the sample space. And that was all well and good if we had a defined sample space and defined outcomes and we could count them. Empirical probability we use more when we actually look at the results of an experiment. And we don't necessarily know the entire sample space. An example of a place that is if you look at, I have no idea why these words are there and they won't go away. It's the M1 if you look at something like insurance statistics and something like what's the probability of somebody who's we don't really have a full sample space of people who drive. We have a sample space of the number of them who have gotten into accidents. And
I don't know if it's just me. I can't hear you.
Yeah, sorry. Still have an audio problem, sorry.
Can you hear me now?
All right, that was fine, yeah.
A little better.
Okay. I'll try to talk more slowly and loudly.
Okay.
But it would be sort of unethical to try to build a sample space of drunk people and seeing if they got into accidents or not. So instead of looking at it as a whole sample space, we look at the results of an experiment. And so we'll say the empirical probability of an event is equal to the number of times the event occurs over the number of times the experiment was performed. And when I look at these questions in my labs, questions frequently contain group. And so in order to try to come up with examples, I took the liberty of downloading a couple of pages from the virtual textbook. Those pages will be in today's notes. Can I turn the page and not lose anybody?
Good.
Okay. So first page from the virtual textbook. In the textbook, if anybody has it, I'm on page 722. And we had looked at theoretical probability. Did anybody want to do more examples of that, of the homework, before we look at that empirical probability? I'm just thinking, we didn't do any like spinner type questions, so let's go through and look at one of those. It says use the spinners shown to answers 41 to 48. Assume that it is equally probable that the pointer will land on any one of the 10 colored regions. If it lands on a border, you'll spin again. So what's the probability on this spinner that you land in a how many are red? Can you guys see my spinner? How many?
Yeah.
3. Out of how many regions are there altogether?
10.
So their probability is 3 out of 10. What's the probability that I land in a yellow region?
That would be 2 out of 10.
2 out of 10.
1/5.
Beautiful.
Oh,
Okay, so those spinner type problems are all right. Another type of problem that I believe I put 1 or 2 of in the homework. Does anybody remember from something like a high school biology class seeing tables like these? It says exercises 49 to 54 deal with sickle cell anemia, an inherited disease in which red blood cells become distorted and deprived of oxygen. 1 in every 500 African-American infants is born with the disease. Only 1 in 100,000 times white infants get the disease. Person with 2 sickle cell genes will have the disease, but a person with only 1 will have a mild form. So little s is the sickle cell gene, big S is a healthy gene. And so first, both parents have only 1 sickle cell, so that they have a mild trait. What's the probability that they give birth to a child who has sickle cell? Can everybody look at this table and see that there are 4 results? The denominator would be 4. And in order to have the disease, they need both the disease genes, so that would be 1 out of 4.
I guess, yeah.
In order to have the trait, we've got those 4 results. To have the trait, they have 1 of each gene, so that would be 2 out of 4, which would be 1. Beautiful. And in order to be healthy, again, there's 4 results. In order to be healthy, they don't have any of the disease genes, so that would give me 1 out of 4. Is everybody comfortable reading a table like that?
I have a question.
Sure.
Has the sickle cell trait, what about that has both parents having the sickle cell trait? Why is that not included in number 50? So,
Oh, in this example, both parents have the sickle cell trait. The first parent has one of each. The second parent has one of each. And so the table shows the different ways that those parents could have children. Because
Okay,
the parent only gives one of their two genes. So there's
thank,
1 in 4 possibility that they don't get it at all. There's 2 in 4 possibilities that they're like the parents and they have the trait. And there's 1 in 4 possibility that they have the disease.
thank you. Yes, thank you.
All right, so now let's look at something that's considered this empirical probability. So I'm looking at this table. It says the table shows the distribution by age and gender of 29.3 million American people alone. Use the data in the table to solve exercises 55 to 60. And so over here, we can look at each person as being an experiment. And so the table represents here a total of 29.3 million people. As we read the table, can everybody see that there's a total of 12.5 million males, a total of 16.8 million females, a total of 1.5 million people who live alone. They're in the age group from 50 to 24. Everybody reads it as 0.8 million females, 0.7 males, and so on. Everybody with me so far?
Yes,
Yeah.
Two of these, what's the probability that I have a female? Well, the total in the table is that 29.3 million. The total number of females is 16.8. And here, because they ask us as a decimal round to the nearest 100, does it make sense that I'm going to grab my calculator, turn it on, take that 16.8 and divide it by the 29.3. And so to the nearest 100, is anybody else getting 0.5? This is the 10th place. This is the 100th place. That next digit was a 3, so I'm going to round down 0.57. Let's look at 58. What's the probability that we have a person in the 35 to 44 range? Again, my total is 29.3. Of the 29.3 million, how many people are in the 35 to 44 range? Is everybody all right? That would be 4.2 million. So now let's change that into a decimal. 4.2 divided by 29.3 gives me 0.14. Is everybody getting the same result?
So 4.2 divided by 29.3. And 0.14. Oh, that's what I got.
Yeah. And then what's the probability that we have a man in the 45 to 64 range? Again, the total number of experiments, our sample space is 29.3 million. How many are men in the 45 to 64 range? Is anybody else getting that to be the 4.3? So when we
I
take
got 0.317.
yeah, you're a Sept. When I do that division, I am getting myself. It would round to 0.5.
0.5.
What did I put in?
Did you-
Oh, wait. Oh, I did the wrong thing. Okay.
Okay. Everybody who's on the meeting that's
Okay.
quiet. Are you guys all right with this?
Yeah, you
Uh,
jumped number
wait.
59.
And I got 0.14 again, not 0.15.
It's 0.146. And because
Yes.
the third digit is bigger than 5, we have to round up at them.
Oh, okay.
Okay, we're using those rounding rules. Did somebody want to see number 59 done out? Did I hear that?
0. Yeah, I did it 0.05.
Okay. You're a step ahead of me, so that's 0.8 over 29.3.
Oh, is it 0.8? Oh,
Oh, no. Yeah, women in the 15 to 24 is 0.8, right?
women.
So
Yeah.
I'm getting
Oh, okay.
0.03 when I round.
Okay, got it.
Okay?
Mm-hmm.
Should we look at another table just to make sure?
Yes.
Okay. When I download pictures from the virtual book, they put that little watermark in the middle. And I hate reading through the watermark, so I'm going to look at this table here that talks about educational attainment in millions of the United States population, ages 25 and older. And so find the probability expressed as a simplified fraction. So this time we're not changing them into decimals, we're reducing fractions, that a randomly selected American age 25 or older has less than 4 years of high school. What would the denominator be for this fraction if it's dealing with that table?
174.
174. Beautiful. And what would be the number of people that have less than 4 years of high school?
29.
29.
And so setting up that fraction all right. And let's do one more. Let's look at 70. A man with 4 years of college or more. The denominator is still the 174. What would be the numerator if I want men with 4 years of college or more?
23.
23. Life is good?
Okay.
Okay.
Mm.
So this idea of empirical probability, all right.
Yes.
Actually, as I'm looking at it, out of the corner of my eye, I saw the target problem. I think there's one like the target problem in the homework.
Yes.
Did you want to try it on your own, or did you want to go over one? Should we look at it?
Sure.
Okay. The target in the figure shown contains 4 squares. If a dart thrown at random hits the target, find the probability that it will land in an orange region. With something like this, does it make sense that the probability that it lands in the orange would be the fraction, the total orange area over the total area of the board?
Okay.
So far, so good.
Mhm.
For the board, B-O-A-R-D, I can spell. Is everybody all right? Area is length times width, so that would be 12 times 12 or 144. So this denominator is 144. How much of it is orange? Does everybody see 2 orange parts?
Yes.
The one in the middle, and then this one that almost looks like a mat in a picture frame.
Yeah.
I think the middle
9.
part is easier. The middle orange. Is 3 by 3, which is 9.
Oh, okay.
But now the other orange
9 by 9.
9 by 9, but it's not the whole 9 by 9 square, is it?
No,
Oh, yeah,
9
there's-
by 9. And then don't we have to take out the 6 by 6?
mhm. So 9 times 9 minus 6. Okay.
So that's 81 minus 36, which I believe is 45. Somebody check me, please.
I got 45, yeah.
So that gives me 9 plus 45 in the numerator. So that gives me 54 over 144. And I think that's pretty reducible. First of all, actually, I think both of those numbers can be, what would you like to divide out of both of them? 2?
definitely 2.
So that gives me 27 over 72. And I think both of those can be divided by 9, which gives me 3/8. Final answer. So we've got our basic definition of probability down. Now, I want to apologize a little bit. I'm using OneNote, the notes on. One skill I have not yet mastered is how to get the pages in the right order. And so we looked at the examples from the e-text. I'd like to add a page, to add just a couple of definition-y things. And then I'd like to go back and look at that probability practice handout, which I believe I told you folks last class that that still is in Blackboard in content and handout. So we're going to go over that today. In general, we said the probability of an event is the number of ways the event can occur over the number of outcomes in the sample space. And so it becomes important to count, to find the number of things in the event and the number of things in the space. We've got the counting principle, which loosely tells us that usually the word and tells us to multiply. And then to help us count, we also have permutations, which are arrangements of distinct objects. How do you spell distinct? D-I-S-T-I-N-C-T. Where there's no repeats and order matters. And we have combinations, which are distinct, no repeats, and order does not matter. And if I'm remembering correctly, that kind of takes care of everything that we've done since we finished looking at sets. So let's go through and see how this works with permutations and combinations. So now I'm going to go to that probability practice problem handout.
Okay.
So first question says, there are 11 girls on a softball team. Amy, Beth, Chris, Deb, Elle, Fran, Jen, Helen, Izzy, Jill, and Katie. The coach needs to pick 11 of the girls to bat in the next game.
9.
In how many, I'm sorry, 9 of the girls, thank you, to bat in the next game. In how many ways did he pick the batting order for the next game? Couple of things in this wording. First of all, is everybody all right if a question asks in how many ways, it means I'm going to have a whole number answer.
Okay.
How many is a counting number? And so now we've got to figure out how to come up with that counting number. You see how it says batting order. So does order matter?
Yes.
Yeah.
Yes. And so that word order implies to me it's going to be a permutation. How many do we have to pick from?
11.
11.
And how many do we want?
9.
9. So 11P9, you can get it from your calculator. For those of you who are calculator less, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the product, 11, 10, 9, 8, 7, 6, 5, 4, 3. Or the product of 9 numbers starting with 11 and working down. And so when I go through and find 11P9, it would help if I could type right. Oh my God, how many are there?
19.
1,995,8,400.
So 19,958,400 different batting orders. Not gonna lie, I made this question up because my kids played ball a lot. And from my experience of those 19 million, almost 20 million ways, none of them will make all of the parents happy.
Right.
Next one says, what's the probability? Is everybody all right? If a question's asking for a probability, it's telling me I should expect my answer to be a fraction.
Okay.
And so what's the probability that Amy will bat third? Does it make sense that the denominator of this fraction would be all of the different lineups, which is 11P9, or that product 11, 10, 9, 8, 7, 6, 5, 4, 3. And I can look at each of those numbers as a place in the lineup. Now, how you figure this out depends on you as an individual. I personally find with questions like this, I find it easiest if I picture filling in the blanks. So those are my 9 spots for the players to go in. With me so far?
Yes.
I want Amy to bat third. How many Amy's are there?
1.
So in this third space, I have 1 person to pick for, right?
Okay.
But now if Amy is there, for the other spaces, how many players do I have left? Don't I have 10?
Yes.
Then 9, then 8, then 7, then 6, then 5, then 4, then 3.
Okay, so
And now, if you were a glutton for punishment, you'd multiply all of that out and see what you get. But as I'm looking at it, I find that it reduces quite nicely, and I'm left with 1 out of 11. Does that make sense?
Yeah.
Now, if you want to be fancy pants about it,
I don't.
that's the technical term, and don't want to fill in the blank, would we say in the numerator, going back to the 11P9, that, whoa,
What happened?
I put my hand down on the touch screen and it
Oh.
opened one of those little doohickey things at the bottom.
Hmm.
So, for the numerator, if I wanted to use permutations, there's one Amy, I want to pick her. And so I'm multiplying. There are 10 other players and I need 8 of them. And so I could also look at that as 1P1 times 10P8 over 11P9. I think if you use the help me solve it function, they're going to do it more that way.
Okay.
I personally find it easier to do it the other way where I'm thinking of filling in the blanks.
Yeah.
Whichever one you prefer, grab a hold of it and use it. But please, with questions like this, I'm looking for work. I'm not just looking for final answers. My heavens. So should we look at C? What's the probability that Beth will be last, Katie will be first, and Chris will be fourth? In order to do this, would you rather use the permutation notation or would you rather expand, pardon me, the product and fill in the blanks?
Can we do both?
Sure. Which do you want to do first?
The fill in the blanks?
So filling in the blanks, there's 11, 10, 9, 8, 7, 6, 5, 4, 3 ways of picking them. Beth is last. How many Beths are there?
1.
1. So in this last space, I have 1 person. Katie's first. In this first place, I have 1 person. Chris is fourth. In this 4th place, I have 1 person. How many batters have I used up?
3.
3. So how many are left?
7.
8. 11 minus 3 would be 8.
Yeah.
So we'd have, whoops, 8, 7, 6, 5, 4, 3 other players to pick. When I reduce, I can cancel out the 3, 4, 5, 6, 7, and 8. When I multiply across in the numerator, 1 times 1 times 1 is 1. In the denominator, 11 times 10 times 9 would give me 990. If I were to try to do that the other way, the permutation way, in the denominator, we already said we have 11P9. In the numerator, we have 1, oops, I'm very sorry, my hand misfired. In the numerator, we have 1 Beth, pardon me, 1P1, and 1 Katie, 1P1, and 1 Chris, 1P1, leaving us with 8 other players to fill in the 5 remaining, no, I'm sorry, 6 remaining spots. What's 9 minus 3? 6. 6 remaining spots. And they should both take you to exactly the same place. How's that one?
I think I'm gonna stick with the filling in the blanks.
Yeah.
strategy.
Most people prefer the fill in the blanks, but I do believe that my labs uses the permutations.
Yeah.
Okay, question 2. Question 2 says there are 7 girls and 5 boys in a class. The teacher wants to pick a group of 6 to work together on a project for the class. Okay, if I'm picking a group to work together, does order matter or not?
No.
No.
Order does not matter. And so over here, because we're picking a group to work together, we're declaring that order does not matter.
Hmm.
If order does not matter, we're not going to be filling in the blanks, because when we fill in the blanks, we're saying that order does matter. It becomes more of a permutation. So here, order does not matter. A says how many. Whoops, I lost the word many when I typed the sheet. Sorry. So is this going to be a whole number or a fraction?
A whole number?
Whole number. If order does not matter, what should I use to figure it out? Combination. How many students does the teacher have to pick from?
7.
Well,
12.
Oh,
How
12.
many is the teacher picking?
6.
6. And so is everybody all right? This would be 12 combination 6. Which gives us, how many ways can the teacher select these 6 kids?
924. That's what I got.
Anybody else get the same? If so, part B says how many ways? So this is also going to be a whole number. Order still does not matter, so it's a combination. We want a group of 6, so we're still selecting 6. But if we only want girls, how many are there to pick from?
7.
7. Does everybody all right? That would be 7 combination 6,
yeah.
which is,
I just got 7.
yep, so did I. Just remember, shortcut 7 combination 6 should be the same as 7 combination 1. Next one says, how many ways? So here again, I'm getting a whole number. Order still does not matter, so it's a combination. We want a group of 6. If we're only picking from the boys, how many are there?
5.
5.
5. Can I do 5 combination 6?
Mm-mm.
No.
No. If there are only 5 boys, is there any way of me getting 6 boys?
No.
No.
No, it's not possible. In how many ways can it happen?
0.
0. And look for it. If something's not possible, there's 0 ways of it occurring.
Okay.
D says how many ways? So again, it's a whole number. We want a group of 6. This time we want 4 girls and 2 boys. Order does not matter, so I'm thinking combination. But help me out here, folks. Will 1 combination be enough?
No.
We need 2.
We need one for boys and one for girls.
We need 1 for the boys and 1 for the girls. The word and tells me I'm going to multiply those 2.
Mhm.
Which would you rather do first? The girls or the boys?
girls.
The girls. How many girls are there? 7, and we want 4. And then for the boys, there are 5, and we want 2. 7 combination 4 is, I think, 35. Can somebody check me on that? Did I get it okay?
Yes.
And then 5 combination 2, I believe, is 10. And so here we have 350 ways. That one all right? Part E is where we put the pieces together. It says, what's the probability? So here I'm expecting fractions. That the teacher gets 6 girls. Well, that would be the number of ways the teacher can get 6 girls over the number of ways the teachers can pick 6. Do we know how many ways the teacher can pick 6 girls?
Uh,
7. And do we know how many
6 out of 7.
How many ways can the teacher pick 6 students? Isn't that our 924? And I do believe that 7 goes into 924. I'm not positive though. So I'm going to double check. Yep. And so that reduces to 1 over 132. Does everybody see how we're taking the preceding answers and putting them together? This would be my entire sample space.
Yeah.
And so what's the probability of getting 6 boys? My sample space is still the 924.
5.
How many ways can I get 6 boys?
0, because
0.
0.
Oh.
So here the final answer is 0. And in the last one, again, my sample space is still that 924. Did we figure out how many ways we can get 4 girls and 2 boys?
350.
350.
350.
350. And so let's see. I think if I divide those by 7, I get 50 over 132. And then if I divide them by 2, I think I get 5 over 60, 25 over 66. So I think that's how that one reduces.
Yeah,
How does that one look?
I got the same stuff.
Does everybody see the difference between the first and second question? The first question order mattered, and the second question order did not matter. Shall we try? Oh, crap.
Holy cow.
My watch. Are we out of time, guys?
Yeah.
Not by much, but yeah.
Okay. Between now and Wednesday, if you could look at the back side of this handout, I'll try to, on my own, on a separate sheet, book the back side out and post it. And I'll have the work all done out before next class, so we don't have to go quite as slowly through it, but we will go through it. Does that sound like an all right plan?
Okay.
Yeah.
Yes.
All right, in which case then I am going to stop sharing my screen, and I am going to stop recording.